Welcome to this explainer. Today, we're going to take a collective deep breath and look at one of the absolutely most elegant ways humans solve massive global challenges. You know, when we think of engineering, we usually picture loud machines, right? Massive concrete dams or fiery rockets. But honestly, some of our greatest, most life-sustaining achievements are completely quiet. They literally happen at the microscopic level, where we gently intervene in natural chemistry to solve problems rather than fighting against them. So today we're demystifying a concept you've probably heard of, but maybe kind of glossed over: reverse osmosis.
So to really get why this tech matters so much, let's start with a super simple, relatable observation. Just picture yourself standing on a beach, looking out at a massive, seemingly endless ocean. It's that classic paradox, isn't it? Water, water everywhere, but no way we can just dip a glass in and drink it. We tend to just accept it as a basic fact of life. But the actual chemistry behind this reality, that's our very first step in understanding how we can solve global water shortages without hitting the panic button. Now, the reason we can't drink it is obviously salt. But actually seeing the numbers puts the sheer scale of this problem into a totally new perspective. We measure this saltiness in something called total dissolved solids, or TDS. For water to be considered fresh water, you know, the kind we can actually safely drink and use in our homes, its TDS needs to be below 500 milligrams per liter. Okay, now compare that to seawater. Seawater boasts a massive salinity of around 35,000 milligrams per liter. I mean, that's not just a little salty, it is overwhelmingly loaded with dissolved mineral salts that our biological and industrial systems simply cannot process.
And that brings us to our ultimate goal: figuring out how to turn those heavily salted drops into pure, safe hydration. Now, for a really long time, this felt like an insurmountable battle against nature. But what if we didn't fight nature at all? What if, instead, we used a clever, quiet manipulation of its own rules to get the water we need? Well, to pull that off, we first need to wrap our heads around the baseline rule that nature itself operates on.
That fundamental rule is called osmosis. In practical terms, osmosis is just the movement of a solvent, like water, between two solutions that have different concentrations. It naturally passes through a semi-permeable membrane, and it always wants to flow from the area of lower concentration to the area of higher concentration. Essentially, think of nature as always wanting to find perfect balance. If you've got incredibly salty water on one side of a barrier and pure water on the other, nature will automatically try to pull the pure water across to dilute the salty side until everything is perfectly equal.
All right, so here is exactly where we step in and gracefully hack that natural system. If nature naturally wants to pull pure water into the salty side to balance things out, we just apply pressure to push it backward. By pressing down firmly on the unfiltered side, we physically force the pure water molecules right through that semi-permeable membrane in the complete opposite direction, effectively leaving all that salt trapped behind.
This binary shift is really the heart of the entire process. Just to recap, in standard osmosis, the flow naturally goes from lower to higher concentration. That's nature's default way of diluting the salt. But in reverse osmosis, human engineering steps in. We apply pressure, causing the flow to reverse, moving from higher concentration back to lower concentration. So while nature quietly pulls one way, we just gently but firmly push the other.
When we actually build this into a physical setup, we use a chamber fitted with that semi-permeable membrane we just talked about. At the top, we introduce the impure brackish water. Then, a hydrostatic piston applies downward pressure. And this physical pressure entirely overcomes that natural osmotic pull, physically forcing the pure water down through the membrane, leaving the heavy, salty brine behind. It's really just a remarkably clean mechanical separation.
So that brings up a crucial question. Exactly how hard do we have to push? Well, to successfully overcome nature's default osmotic pressure, the system requires a hydrostatic pressure of 15 to 40 kilograms per square centimeter. That single metric is the exact amount of force needed to literally reverse the flow of the ocean. It's a significant amount of pressure, for sure, but it's applied in such a beautifully controlled, steady way that the whole process operates safely and seamlessly.
Of course, absolutely none of this works without the true heroes of the system, the membranes themselves. You might hear some intense chemical names tossed around, things like cellulose acetate or polyamide polymers. Don't worry, you really don't need to memorize the chemistry here. You just need to know that these are incredibly thin superfilters. They're engineered at the molecular level to let tiny water molecules slip right through, while catching all the microscopic impurities and heavy salts doing the heavy lifting.
And honestly, the real-world performance of these superfilters is all about quiet reliability. Reverse osmosis removes ionic matter, high molecular weight organics, and even colloidal particles, which are just microscopic substances suspended in the liquid. Basically, they catch almost everything. And despite dealing with all that high pressure, these membranes have a surprisingly long lifespan of about 2 years. They offer low operating costs, incredible reliability, and, when a membrane does finally wear out, it can be swapped out in just a few minutes, ensuring a steady, uninterrupted water supply for everyone who relies on it.
So, when you strip away all the complex engineering, the chemistry, and the massive industrial scale, what we're really looking at is a profoundly beautiful human achievement. A totally simple, calculated change in pressure quietly provides safe drinking water to millions of people around the globe, especially in arid regions where fresh water is terrifyingly scarce. It's a gentle hack that sustains life, operating quietly in the background of our modern world.
As we wrap up this explainer, I kind of want to leave you with a peaceful thought. We are constantly surrounded by hidden science that makes everyday life possible. So, the next time you fill up a glass of water, will you think about the invisible engineering that keeps it full? That quiet, microscopic push against nature that turns the undrinkable ocean into the pure hydration that literally sustains us? Thank you so much for joining me for this focused look at reverse osmosis. Keep asking questions, and definitely keep exploring the incredible science all around you.